Hey, welcome back to chemistry. And so we're continuing on through chapter 6, which is on the chapter of thermochemistry. So now in this presentation, what I want to do is talk a little bit about what heat and work are. So these are words that you probably have commonly heard, but in the context of thermochemistry, they have a very specific definition, which I'm going to bring up here on this slide. So what heat and work are, they're both two forms of energy. But here's the thing, they are not forms of energy that are found in a certain kind of matter. Rather, they are forms of energy that are transferred from one kind of matter to another kind of matter. And usually the first kind of matter that these forms of energy are leaving would be the system, and then the kind of matter that it's going to would be the surroundings. So again, heat and work are two forms of energy, but they're not really energy found in a certain kind of matter. Rather, they are energy that is transferred from one kind of matter to another. So to explain this idea, I've sort of drawn this little picture on the light board that I want to go over with you. Okay, so why don't we pretend that you are out camping, and so you have set up your campground here. And so here we have your tent here, and here are some trees I've drawn in the background, and I have the ground here, and then I have a fire pit here. And so what you want to do is you want to burn some logs for warmth. So this is how you might do that. So you're going to put, for example, maybe 4 logs here. So I'm drawing 4 logs here in this fire pit. Now, you know that after you burn the logs, you will not have much of the logs anymore. In fact, you'll have not much of anything except for a bunch of ashes here. And you sort of know in this process of going from intact logs to ashes that you're going to have energy release in the process. And so now what I want to do is sort of give you sort of the nerdy chemist perspective of how this process occurs. Okay, so let's look at this situation before we have caught the logs on fire. So first, let's go ahead and define a system to look at. So the system that we're going to look at are the 4 logs here. So I'm going to write system here. And then I'm going to draw a line here that indicates a boundary. And this boundary is just the surface of the logs. And then everything outside of the logs is the surroundings. Now, one thing that's going to happen is we're going to burn these logs, and then this system will decompose from logs to ashes. And so the system is still here after we burn them, but now the system is ashes. And then outside the system here, after you burn the logs, you still have the surroundings. They are still here. Okay, so now let's talk about how much energy may be in these logs. And so that may sound kind of strange that I'm saying that there's going to be energy in these logs, but here's something to keep in mind. Logs are made of carbohydrates, and so carbohydrates are found everywhere and they can serve as a fuel source. So an example of a carbohydrate that we're used to is the sugar found in Hershey bars, for example. So if you look at the back label of a Hershey bar, that will tell you how much energy is in that Hershey bar. That energy is due to the carbohydrates in the Hershey bar, and it's going to be about 250 calories. Now, logs also have carbohydrates, but they're a little bit different. The carbohydrates are structured slightly differently, and so the carbohydrates in the logs are not sugar molecules. Instead, they're molecules of cellulose, but they have about the same amount of energy content. But we have a lot more carbohydrates in 4 logs than we do have in a Hershey bar, so there's going to be a lot of energy here. So just for this example, let me just assign a value to the amount of energy in these 4 logs. And let me just say, for example, I'm kind of making this up, I'm just making a guess, that maybe within these 4 logs, there are 500,000 calories worth of energy. We'll talk a little bit more about the calorie unit for energy later, but let's just say we have 500,000 calories in these logs, which is 500 kilocalories. So I'm going to write 500 kilocalories here. Now, After we burn the logs, you know that most of the mass of the logs will go away. and that you're left with ashes. And the reason why most of the mass goes away is because a lot of the mass is leaving the logs in the form of gaseous molecules like carbon dioxide and water. So what you're left with after you burn the logs is ashes. Now ashes are made of mostly just carbon atoms, and they have a lot less energy content than the logs. Now you may remember what I was telling you before, that different kinds of molecules have different amounts of energy content. It happens to be because carbohydrates have the elements that they have, carbon, hydrogen, oxygen, and the structures that they happen to have a lot of energy content. But when you remove carbon dioxide, water from the carbohydrates and you're just left with carbon atoms, they have far less energy content. So maybe in this example, say after burning the logs, where you don't have 500 kilocalories anymore, we have 5 kcal. So we have lost in this process 495 kilocalories of energy. So where did that energy go? Okay, so let's say you're back here before and you decide to burn the logs. So you light the logs on fire, and so I'm going to draw a line here, and they're burning away. And so we know that the 500 kilocalories of energy in those logs will be lost. So when the energy, or rather the logs, are being burned, we're going to have to lose 495 kilocalories of energy. So most of that energy that is going to be leaving the logs and go off into the surroundings is going to be heat. But a little bit of the energy leaving the logs and going off into the surroundings is work. Now, I don't know exactly what proportion of the energy is going to be heat, what proportion is work, but let me just make up some numbers. And so we need to lose 495 kilocalories of energy. And so we'll say with heat, you lose 490 kilocalories of energy, and work, you have lost 5 kilocalories of energy. So now let's step back and see what's kind of important here. I want you to notice that heat and work are not so much energy that is found within the matter. It is not found, for example, you don't find heat and work found within the logs. Instead, this is the energy, the heat and work, that is transferred from one kind of matter, the system, out into another kind of matter, the surroundings. Okay, so let us move on. We're going to do some stuff here on the computer. Okay, so now what I want to do is talk a little bit more about heat. So you need to know, first off, not only that heat is a form of energy that is not so much found in matter, but is transferred from one kind of matter to another. You need to know under what conditions heat is transferred from one kind of matter to another. And those conditions are always when you have a hot object touching a cold object. Heat is always transferred from a hot object to a cold object, but not in reverse. You will never have heat energy transferred from a cold object to a hot object. So to give you a sense of what's going on here, imagine we have two blocks, which I've drawn here. And so we have this hot block here. And so the hot block is labeled H for hot. And then we have separated immediately from it a block which is cooler. So this is called an L block, I guess L for lower temperature. So now the hot block has something that the lower block does not have. Now it's not so much heat that it has more of. Instead, it has more thermal energy. It is the thermal energy in the hot block that makes it a high temperature. It is less thermal energy in the cooler block that gives it a low temperature. Now, when you touch the hot block to the low block here, what happens, you know from experience, is that the hot block will lose temperature. It will cool down, but the cooler block will gain temperature. It will warm up. And then finally, if you leave the hot block and the cool block together, you will eventually get to a point where you have the two blocks at absolutely the same temperature. And when that occurs, then those blocks are said to be at thermal equilibrium. So the question is this: we had a hot block and a cool block, and you know that something must have left the hot block and gone into the cool block. So what must have been that something to make the hot block less hot and the cooler block warmer? Well, that something here was heat. So again, heat isn't so much energy that is found in particular kind of matter. Again, heat is not so much energy found in some kind of matter. Rather, it's the energy that is transferred from a hot object to a cool object, as we saw in this sort of example here. Now, one thing also that's kind of important to point out is that let's just pretend that this H block here is the system. So this is the system. And this L block, this cooler block, is the surroundings. One of the things I want you to sort of note is that when heat leaves the hot block, which is the system, and goes into the cool block, which is the surroundings, you will have as much heat gained by the cool block, which is the surroundings, that is lost from the hot block, which is the system. And so this is pretty much consistent with the law of conservation of energy. So I kind of point out here, very importantly, that heat energy always leaves a hot object and goes to a cold object, but it never goes from a cold object to a hot object. One thing you also sort of need to know is that you will be able to quantify heat, and the letter that we use to quantify that is the letter Q, and the units we use to quantify heat or energy in general are calories. Now, sometimes heat is quantified with a different unit called joules, and we'll talk a little bit more about that in a bit. Okay, so not only is heat a form of energy that leaves one object and goes into another, but there's another form of energy as well, and this form is called work. So I need to talk a little bit about what work is. So to sort of explain work, let's just use a sort of a simple example. So let's say you are mowing a lawn. So here you are. You are mowing a lawn. Let's say that you are the system. Now, the lawnmower here is the surroundings. And so one of the things that you know is if you're actively pushing the lawnmower, you are losing energy, and then any energy that you have lost is being gained by the lawnmower. So the question is, what is the name of that energy that is being transferred from you, that is losing it, to the lawnmower that is gaining it? The name of the energy that is being transferred in this case is called work energy, or just work. So now, what is the value or the magnitude of work dependent on? So you actually probably know the answer to this from experience. So let's say you were not pushing the lawnmower at all, and so you were just kind of sitting there with the lawnmower. My question to you is this: are you losing energy, and is the lawnmower gaining energy? No, neither of these things are happening. And so in order for energy to leave you and go into the lawnmower, what must happen is that you must actively push the lawnmower. When you're pushing something, you're applying a force to that object. So a requirement for a value of work is the amount of force that you're applying onto that object. And so the letter for the force is F. Now, another thing you maybe know from experience is that not only do you have to push the lawnmower with a certain force to lose energy, but you know that the more distance that you push the lawnmower, the more energy that you lose, and the more energy that is gained by the lawnmower. And so work, for this reason, is going to be dependent not only on the force that you give the lawnmowers, but it's also going to be dependent on the distance that you push the lawnmower. So in physics and in this class, work, the value of it is the force that you're applying on the surroundings times the distance which you push it. One other thing you'll learn later on in this class is that work can be defined in terms of a force that a system is pushing on a surroundings and the distance that you're pushing it, but it also can be determined by say, a gas and the volume that is expanding and how much pressure that volume is expanding against. So work is measured in joules, and any work joules that are transferred to the surroundings, which are the mower, must be lost by the system, which is the person. So now what I want to do is talk about the units for energy. And so one of the units of energy is joules, and the other unit is calories. And so what we just kind of mentioned before is that joules was originally defined to describe a value or magnitude for work, but now we use joules to describe a value or magnitude for work and energy in general. And so Joules is the SI unit for energy. On the other hand, calories, which is also used to describe units for energy, is not an SI unit for energy. So importantly, joules is not a base unit, but instead joules is a derived unit. And the reason why is because this derived unit is derived from base units. And so let me talk about how that occurs. So one of the things we just kind of talked about is that work is equal to force times distance in that previous example. Now, if you take a physics class, you will probably learn that the force on an object is going to be equal to the mass of the object times its acceleration. So if you substitute here mass times acceleration into force into this first equation, you get this equation, that work is equal to mass times accelerations times distance. And so let's talk about how we derive joules here. So again, work is equal to mass times acceleration times distance. And so mass here is going to be equal to kilograms. Acceleration, you might learn in physics, the units for that are meters per second squared. And then distance is meters. And so if you combine these units, what you're going to have is kilograms meters squared over seconds squared. And so these base units here, when you multiply kilograms times meters per second squared times meters, these base units, when combined together, are called the joule. So you can see that the joule here is derived from these base units. Now, another unit which you can use to describe energy is the calorie. So the calorie was originally described the amount of heat that was needed to warm up 1 gram of water by 1 degree Celsius. We often use calories as units for energy, but they are not the SI unit for energy. And so usually in problems, what you have to do is convert energies perhaps out of calories and into joules. But again, we use calories a lot of the time in problems. And so a way to think about this is that a liter is not an SI unit for volume, but we often use liters to describe volumes. While the meter cubed is an SI unit for volume, in a similar fashion, calories is not an SI unit for energy, but we constantly use calories to describe energy. But in the end, we'll probably convert calories into joules. Okay. Now, one thing that we do know is that joules is derived from work, and it's a form of energy, and calories is derived from heat, which is a form of energy. And so basically there must probably be, since they're both forms of energy, an equivalency between the value of a calorie and the value of a joule. And you can sort of see that here on the bottom side of the slide here, and that since they're both forms of energy, it has been determined that 1 calorie is going to be equal to 4.184 joules. So when you're solving problems, one of the things you're going to have to do is be able to convert calories to joules. So I have that here, and so again, this will probably be given to you for the test, and that you need to know that 1 calorie is equal to 4.184 joules. Now, another important conversion you need to know is you need to know that there's another different kind of calorie, which is called a dietary calorie, which is different than the regular calories we use in these problems, which is called the scientific calorie. And so 1 dietary calorie is equal to 1,000 scientific calories. And so, for example, when I was talking about the Hershey bar before being 250 calories, those were dietary calories. And so that would be 250,000 scientific calories. Okay, so let's go ahead and practice some problems on the board to get used to these conversions. So I'm going to the light board. Okay, so let's try problem 1. So if problem 1 is, how many scientific calories and dietary calories are found in a Hershey's Kiss, which contains 9.2 times 10 to the 4 joules of energy? Okay, so we have 9.2 times 10 to the 4 joules of energy in a Hershey's Kiss. And so what we're going to have to do is first figure out how many regular calories this amounts to, and those regular calories would be scientific calories. And then once we figure that out, we'll figure out how many dietary calories are in this value. So converting this to regular calories is pretty simple. Again, I think on the test you will be told that 1 calorie is equal to 4.184 joules. But to solve, to get this into calories, all you have to do is take 1 calorie over 4.184 joules, and that should give you the answer. And I worked it out earlier on my calculator, and I got 21,998 calories, but it looks like this is going to be rounded to 2 significant figures. And so this would be just 22,000 calories, or 2.2 times 10 to the 4 calories. Okay, now what you may be asked to figure out instead is if you have a value in joules, you might have to figure out how many dietary calories are in this value. So let me show you how to do that. So the way you do that is we're starting out with joules again, which is 9.2 times 10 to the 4 joules. And then what we're going to do is multiply this by 1 calorie over 4.184 joules. And so now you can see that the joules cancel out and we're now in just regular calories. But remember, if we want to convert this into dietary calories, we have to remind ourselves that that's different than just regular calories. And so you have to remind yourself that in 1 dietary calorie, you have 1,000 regular calories. So what I'm going to do is I'm going to write here times 1 dietary calorie. And to symbolize dietary calories, to show that it's different than regular calories, I use a capital C here, like this. So this is 1 dietary calorie. And then this is going to be over 1,000 regular calories. And so it looks like the regular calories cancels out, and you'll get an answer in dietary calories. And I think if you work that out, rounded to correct number of significant figures, then the answer you should get is going to be 22 dietary calories. So very importantly, a Hershey's Kiss has 9.2 times 10 to the 4 joules, which amounts to about 22,000 regular scientific calories, which is 22 dietary calories. Okay, so let's move on to the second problem. Okay, second problem, a little trickier. And it says, a Snickers bar, which has a mass of 44 grams, has 250 dietary calories. Convert this to kilojoules per gram Snickers bar. Okay, so this is a little bit trickier. So we're having a Snickers bar. We're told the mass of the Snickers bar is 44 grams. We may use that information later. And that total Snickers bar has 215 dietary calories. So let me write 215 dietary calories. So to indicate that we have a dietary calorie, I use a capital C and then AL. Now we want to get this into kilojoules, but that won't be far enough. We're going to have to convert this kilojoules value for the entire Snickers bar into kilojoules per gram of Snickers bar. So we're going to have to get to that point eventually. But first, let's go ahead and take these 215 dietary calories, which are in the Snickers bar, and let's just get this into kilojoules. How would we go about doing that? Well, the way I would go about this is I would first convert dietary calories to scientific calories. So you might remember that 1 dietary calorie is equal to 1,000 scientific calories. Okay, so once we have it into a regular scientific calorie, we can then convert it to joules. So we can convert calories into joules. And so there are 4.184 joules in 1 calorie. And then final step will be to convert joules to kilojoules. And so here, just reminding yourself that there are 1,000 joules in 1 kilojoule. Now let's go ahead and set that up and see where we're at. So we get 215 dietary calories, and we're going to get this into regular calories. And so I'm going to times 1,000 regular calories over 1 dietary calorie. So you can see the dietary calories cancel out, and we're at regular calories. And now what I want to do is get regular calories into joules. So it's going to be times 4.184 joules over 1 regular calorie. So that's pretty easy, right? So now we're in joules. Let's get that into kilojoules. It's going to be times 1 kilojoule over 1,000 joules. And so the joules cancels out, and so we should have an answer in kilojoules. And so when I worked this out earlier on my calculator, I'm just going to throw in all the numbers I got in my calculator, which is 899.56 kilojoules. But here's the thing, we're not really done with the problem yet. And the reason is I have just worked out the total energy in kilojoules that is in this full Hershey bar. But what we want to know is the kilojoules per gram of Hershey bar. So to figure out the kilojoules per gram of Hershey bar, in other words, how many kilojoules there are in 1 gram of Hershey bar, you have to take the total amount of kilojoules in the Hershey bar and divide it by the total mass of the Hershey bar. And that will tell you the total energy per gram of Hershey bar. So we're going to do this value here. You're going to divide it by 44 grams of the, I should be saying Snickers bar. And so the answer you get here, I think if you work this out, is 20 kilojoules per gram of Snickers bar. Okay, thank you for listening to that. We'll see you next time.